Okay, so I repeat. I would like to start with the definition from the previous lecture, the algebra of shifted symmetric functions. So I recall the definition. It is a projective limit of the algebras of shifted symmetric polynomials in n variables. And this limit is taken in the category of filtered algebras, which essentially means that the degree of the polynomials remains bounded. And I recall the definition of the shifted symmetric polynomials. So this algebra of shifted symmetric polynomials, in n letters, say x1 and so on, xn, is defined as the subalgebra. It is the subalgebra. It lies inside the algebra. Take, say, the ground field, the complex number. It's not very important. And with the property that if our polynomial should be symmetric, in shifted variables, after a shift, in shifted variables, so say x tilde, which is by definition xi minus I and plus a constant. C is a constant, and the value of this constant does not matter. We can choose it arbitrarily. The definition does not depend on this choice. And next we have to define the projection. The projections of n variables, polynomials to polynomials in n minus 1 variables. It is as before, specialization of the last variable of xn to 0. So we take, this means that an element of algebra of shifted symmetric functions is by definition the sequence, infinite sequence, such that the component number small n, or maybe it's better to write my notation, sorry, Fn belongs to the algebra of shifted symmetric polynomials, and if we specialize the last variable to 0, we get the preceding polynomial, and the condition in the category of filtered algebras means that the degree does not grow. And actually it should stabilize. Okay, so this is the definition, and the first result is as follows. So some examples. The simple example is as follows. Example. This is analog of power sums. So the power sums, I will denoted by star and a constant C. It depends, the definition depends on the choice of this C. Is as follows. I will write in infinitely many variables the definition. It goes as follows. It is by definition the infinite sum of xi minus I plus c to the power k, and minus this expression. And this, it is a formal expression. What does it mean? Please look at this expression. If, first of all, we remark that this expression is formally shifted symmetric because it becomes symmetric in the shifted variables, but it satisfies our compatibility expression, meaning that if some xi equals 0, then the corresponding summand here vanishes. So in particular, this means that more precisely, if you want to define a polynomial, the definition is the same, only the sum is from I from 1 to n. And then we see that putting the last variable equals to 0, we get the similar polynomial, but in n minus 1 variables. So this is a well-defined element. So this is a well-defined element of our algebra. And we can conclude that the whole algebra is isomorphic to the algebra of polynomials in these elements. For any fixed C. Why? The idea is as follows. It requires some proof, but it is not difficult, almost obvious, I think. So the idea is that our algebra, being a filtered algebra, one can prove that the associated graded algebra is canonically isomorphic to the algebra of symmetric functions. So a little bit informally, one can say that the top degree term of this element, top degree term as an element of the algebra of symmetric functions, it is just the ordinary power sum. As a corollary, some corollary which is not completely evident, corollary is as follows, that our algebra can be embedded, is contained in the algebra of formal power series. This is because these elements can be viewed as are correctly defined as formal power series, and this is because the constant term here does not accumulate. It is equal to 0 simply. Okay. Is it correct? Yes, I think it's correct. it's correct. This seems a little bit strange, but it seems to be correct. What next? And I recall the result from the previous, this is a reminder from the previous lecture. The result is as follows. So assume mu is a Young diagram with m boxes, and lambda is another diagram, and n is greater than m, then we have the following result. This is my notation for the falling factorial power. And this is the number of paths in the Young graph from mu to lambda, and divided by the dimension of lambda. And the resulting expression is the shifted Schur function indexed by mu in these variables. And I would like to say that by the very definition, any shifted symmetric function can be viewed as a true function in infinitely many variables, provided that almost all variables are equal to 0. Then the result of substitution, as here, has a meaning, makes sense. And I recall the definition, maybe I will recall it a little bit later. This is some natural analog of Schur functions with some shifts, and we replace the ordinary powers by falling factorial powers. And again, we have here that informally that the top degree term is the ordinary symmetric function. So what does it mean? We have that this element is contained in the filtration term of degree less or equal to m, and then after factorization, so we have this map to the quotient space. And this is canonically isomorphic to the m degree component in the algebra of symmetric functions. And under this map, this is just the image here in this homogeneous component, and the claim is that we get a conventional Schur function. It's easily verified from the definition of this object. So this was essentially the reminder. And now some next results. Today I would like to discuss some remarkable object, which I call the algebra A, the algebra A of regular functions on the set of Young diagrams. So what is the definition? I recall some old result from lecture 4, I think, as follows. Let's consider the so-called characteristic function of a Young diagram. So let lambda be a Young diagram, a partition, and u be a complex variable. Then this is by definition the following. Formally infinite product u minus lambda I plus I minus 1/2. And here a similar expression with lambda equal to 0. Formally, we take the product from 1 to infinity, but actually almost all terms here are equal to 1. So the product is essentially, is in fact finite, makes sense. And this is some rational function. This is some rational function. Rational function in the variable u. And moreover, it is regular at the infinity, and even more, the value at infinity equals 1. So it's easy to see why this happens. And I recall that this expression can be written in a different way as a finite product from D. D is the number of diagonal boxes. And these are modified Frobenius coordinates. So the ordinary Frobenius coordinates plus 1/2. And what I want to say, so because this function is regular at infinity and has the definition, sorry, is as follows. The definition R is a subalgebra in the algebra of functions, which is generated by Taylor coefficients of the expansion of our function at infinity. It is more convenient to take the Taylor coefficients not of the function itself, but of its logarithm. This is the same, because if you have a function which equals 1, and we take the expansion of it, the coefficients of this in this expansion and the coefficients in the expansion of the logarithm generate the same algebra of functions. Here they become algebras, or they become functions in lambda, which here appears as a parameter. So what we want to have, what you want. We want to write this as a sum, some coefficients, and the sum goes. So this is a formal power series in the inverse powers of u, because we want to deal with u equal to infinity. And we look at these coefficients, and these coefficients are some expressions which depend on lambda, and these are some functions in lambda, and we want to deal with the resulting functions which are generated by these coefficients. But look what happens. What are these coefficients? It's easy to see. Just look at this expression and slightly rewrite it. So what we have to take the logarithm of a product of what we have here, a similar expression, only with lambda equal to 0. So we take And if we write this, we get exactly the sum okay? And this is the same as sorry. As follows. So the coefficients what we want are shifted power sums with c equal to 1/2. Okay. So we can conclude from this that our algebra is isomorphic to the algebra of shifted symmetric functions in the variables lambda1, lambda2, and so on and so on. This is because we simply the only thing.
Shouldn't we divide by k in the expression of logarithm?
Sorry?
Shouldn't we divide by k in expression of logarithm into Taylor series?
Yes, you are right. You are right. You are right. Thank you. Indeed. Thank you. Of course, you are right. But nevertheless, the result is as follows. Up to this factor, the coefficients are these analogs of power sums. So we get this isomorphism. The only fact, maybe, the only additional fact to be proved is that these functions are algebraically independent, but this is obvious. So we get indeed this isomorphism. But now look at this expression and do the same, but taking this expression, what we get? Then we get that the same logarithm can be written as follows, as some okay. Just the same argument, same picture. This can be written as this is the same, but sometimes it is more convenient to realize with plus minus a sign as follows. So we see, now we see that, so the conclusion is as follows. Elements, so we can say that elements of our algebra are shifted symmetric functions, shifted symmetric functions in the coordinates, in the raw coordinates. But they are also supersymmetric, supersymmetric functions in modified Frobenius coordinates. Frobenius coordinates. Because the same coefficients can be written in this way. And I recall the definition of the algebra of supersymmetric functions. So the algebra of supersymmetric functions. It can be defined again as a projective limit in the category of graded algebras. We can take the algebras of supersymmetric polynomials in m/n variables, and here we have a double limit. One can take m is equal to n, it does not matter, and these are, this algebra is generated by supersymmetric polynomials which is the sum of in x's minus, maybe it's better to write again sum, another sum. If you want infinitely many variables, we take from m to n, and in infinitely many variables, we take formal sums in infinitely many x's and infinitely many y's. But as I explained before, this algebra is only another realization of the algebra of symmetric functions. We only take some super specialization of the ordinary symmetric functions simply by saying that the power sums are realized as supersymmetric power sums, and that's all. But what we get, so we conclude our algebra of regular functions, our algebra A has several realizations. First, it is the algebra of shifted symmetric functions. Next, it becomes from another viewpoint. We just turn the picture and we obtained the algebra of supersymmetric functions. And next, the next remark is that our A is also algebra of shifted symmetric functions. again shifted symmetric functions in the coordinates, in the column coordinates. Namely, what I would like to say that A, item S, A is stable under the change of variables. If you replace lambda by lambda transpose, we get the same algebra of functions. Why? And this is because from the definition. So look again at this picture. It's not evident from this, but becomes evident from this formula, because transposition of Young diagrams boils down to interchanging A and B Frobenius coordinates. And when we get, this is because we have lambda transpose U is equal to 1 over F lambda, and only we change U by minus U. And this change of sign here just amounts, so if you, when we reverse this and this, and we need only to change the sign here, and this is the same as changing the sign in U, and this gives us the relation which is not completely obvious from the initial definition, that is equal to lambda, sorry. Lambda transpose. So we see that the definition is well balanced. What next?
Excuse me, and
Sorry.
when you say
This
that,
is not for one half.
Oh, all right.
One half, sorry. It's not true for arbitrary C, but it's true for one half. Okay. But this is not the end. There is one more realization of the same algebra of regular functions. It goes as follows. So I need some definition. Maybe I already gave it or not. I don't remember, but anyway. So the notion of content of a box. So if you have a box, it is by definition the difference between the column index and the row index. So we get this picture. So the content is equal 0, 0, 0, 1, 1, 1, minus 1, minus 1, minus 1, minus 2, minus 2, minus 3, 2, 2, 2, and so on, and so on. And the definition now is as follows. Let's introduce one more system of functions as follows. Pi k lambda is equal to the sum over all boxes. You take the content raised to power k. And here k takes the values 0, 1, 2, and so on. Why 0? Because the definition makes sense for k equal to 0. It's quite reasonable. It's simply the number of boxes. And you want to have a number of boxes because this is the first function, the first regular function. And now the result is as follows. Some proposition. So the algebra A of regular functions can be viewed as the algebra of polynomials in these elements. So what is said here? So first,
Excuse me, could you please repeat what is C?
C is the content of a box.
Thank you.
C is the content. I did not introduce the definition. Yes, excuse me. You are completely right. So maybe I have to write. So we have a Young diagram. So we have a Young diagram. We have finitely many boxes. We look at the contents and raise them to power k and take the sum. So this resembles the definition of the power sum functions, and we will see that is some analog, one more analog of power sum function. So the proposition says that first, these elements are inside this algebra. Next, they are algebraically independent. And finally, they generate the whole algebra, so it can be viewed as the algebra of polynomials in these variables. How to prove this? So the proof. The idea is first to slightly modify the definition. Modify the definition of these elements. As follows. So I introduce some modified version. I want to replace these elements with future generators by some other generators which are closely related to them, but which are more convenient for us. These are as follows. So I will denote it as pi k tilde. And the definition is as follows. We take again the sum of the boxes and the content. But what we have, I want to subtract 1/2. And next, I want to take the foreign factorial power, not the ordinary power. Okay. This is not very, this does not change the result, because we obviously have that these new elements, it is in the linear span of pk, pi k minus 1, and so on, till pi 0. And it can be written as follows. It's simply pi k plus lower terms. Lower terms. This is obvious, I think, from this formula. From this formula, it should be obvious because factorial powers satisfy the transition from ordinary powers to factorial powers if is of the same kind, and this shift is also produces again some transformation, some unitriangular transformation of again of the same type. So in our claim we can replace these elements by these modified elements. So actually I will prove the same claim but for these modified elements, which will be easier. Why? You will see. So I will claim, I will prove, I'm going to prove that our algebra is the algebra of polynomials in modified elements. How to do this? How to do this? I need a lemma. Some lemma. It says the following. So suppose S and T are some numbers. But I want that T minus S is a non-negative integer. Non-negative integer. And then I claim the following. The sum of x to power 4 in factorial power. Sum goes from x equal to s till x equal to t. I mean the sum, we substitute x equal to s plus 1, s plus 2, and so on, till s equal to t, which means, which makes sense because I assume that the difference is a positive and non-negative integer. And the claim now is that it is equal to t plus 1 to k minus s to k. So look at this. What this means? This is some difference analog of integration formula, the Newton-Leibniz formula, because this is just some discrete analog. This is a discrete analog. Discrete analog of what? The formula from integral from s to t, k xk minus 1 dx is equal to tk minus sk. Okay. So there are some modifications because first I want, this is some discrete analog, so I have to assume this condition. There is some shift here, and the powers here are not ordinary, but fully factorial, but it is in the same, of the same type. And actually this is a true analog, because if you replace the factorial powers by ordinary powers, we don't don't have such a nice formula. Becomes more complicated, more involved with some terms of lower degree. And this shows that the factorial powers, in a certain sense, are better than ordinary powers because of this beautiful formula. Okay? So now I want to use this formula, and I want to use it as follows. So what I have to do now, let's look at, so first of all, I'm sorry, how to prove this? So how to prove this? Proof of a lemma, proof of lemma. It's simple, but instructive, because take the particular case, the simplest case, when the difference between T and S equals just 1. So what we get? We want to assume. So I want to prove that particular case, particular simplest case, C minus S equal 1. Now we have to prove that so why it is, but it's easy. So look, the right-hand side, look as follows. We take the product this, x, and x minus 1, and minus x minus 1, is it correct? If k factor plus 1, yes, it's correct. It's correct. And this is just equal to x minus 1, x. So we take this part here, and this part here. So we get okay. And this is equal to x k minus 1, and this is equal to k. Okay. So I proved this formula. So this implies this result. And then to get the formula in full generality is just to sum this expression, and we get this one. So this is easy. So I think it's why I give this proof. It's maybe it's too easy, but just to memorize it, because what we have to memorize, I think, just this relation. You see, this simple argument. Okay, it's easy to understand it. So now I want to use the lemma to prove our result. I recall what is the result. The result is about I want to prove this. So look at these expressions. So return.
Sorry.
Okay.
The lower limit of your integration should be from s, I think, not from 1.
But this is continuous. This is some continuous version. This is continuous version. It's not a direct one. So we have to imagine that to get. So if you want, for instance, to
so on the left hand side there is okay. I understand.
if you
Thank
want,
you.
for instance, if you want to deduce this fact from this one, what we have to do? We have to take some rescaling of variables, and after this rescaling, the factorial powers will turn to ordinary powers, and this shift will become very, very little, disappear in the limit. Okay. So return to proposition. Proposition, I mean that our algebra is the algebra of polynomials and the modified by functions. So we have to take, so I want to take, so I assume that k start from 1. And I have to consider maybe and what I want to prove, I want to prove this. I want to prove that this equals to if I prove this, the result will be obtained. Why? Because we know what we know. We know that our algebra, A, is generated by these expressions, almost these ones, with ordinary powers instead of factorial ones. But if you change to factorial powers, the result will be the same, for the same reasons as I explained before, because these elements are related to the elements with the ordinary powers by some unitriangular transformations, which does not change anything from our problem. So these are algebraically independent generators. And so it's enough to prove this relation. And how to prove it? The idea, there is a little trick. So what we have, what is the left-hand side? The left-hand side is the sum of the boxes. We have to take the content, subtract 1/2, and take this factorial powers. And now the idea is as follows. Let's partition this sum. Let's represent, so the idea, the trick. Right. the sum as the sum over principal hooks. What does this mean? What are principal hook? So we have our Young diagram. So principal hook is this one, this one, this one, and so on. So these are hooks which corresponds to the diagonal boxes. Okay. And what happens with the contents inside the principal hooks? Take this one, this content, the contents, inside the first principal hook range from minus B1, sorry, the first Frobenius coordinates, to A1. So these are and likewise in the ith hook, where I ranges from D, we have the string to this one. Okay. So what we have next? Next, we apply our lemma. And we get, because we have factorial powers, we can easily get this sum, and we get the difference of the extreme values of the contents. And due to this, but then we get the sum like this one. Without minus 5, we would get this. But due to this shift, this little shift, you see there is some asymmetry here, because we have here +1 and here there is nothing to do. Okay, but due to this little shift, we get a complete symmetry. And due to shift, we get so this 1/2 is very important, very important. It guarantees the balance between among the rows and columns. So look, we have 4 realizations: shifted symmetric function in the row coordinates, shifted symmetric functions in the column coordinates. Next, we have supersymmetric functions in modified Frobenius coordinates. Next, we have this power symmetric functions in the contents. Okay, but important remark is that we have some shift in degree. You see what I have to show, this one, okay? Okay. So on the right-hand side, you have an element of degree k, but on the left, we have the index k minus 1. And this corresponds to the fact that we start the indexation of this pi function from 0 and not from 1, because already the first, namely the element with index 0, already gives an element of degree 1, the number of boxes, which is an element of degree 1. So this is quite reasonable. So we have, in some sense, the most natural power sum analog in some sense, but with the price of this modification, with some shift in indexation. But this is not the end. This is not the end of the story. There is a truly remarkable invention by Sergei Kirov. Sergei Kirov. He was a truly remarkable mathematician, my good friend, colleague, and he invented some new system of coordinates, which I call Kirov's coordinates. Kirov's coordinates. Coordinates of Young diagrams. What are they? So look again on this picture and right. So assume that with some Young diagram, so something like this. Some picture like this, okay? Because in general, the diagram can have multiple rows and multiple columns. So in general, we have something like this. Okay? And these diagrams have inner corners, these are inner corners, and outer corners, okay? And the number of inner corners is equal to the number of outer corners plus 1. So this is related to one of the problems, one of the exercises that I gave you. And the idea is follows. So look at these points and take their contents. The contents of a point, some content is just j minus 1. So assume that this is the ix and this is the jx. Okay? So just take the difference of the coordinates. And so let x say r. These are contents of inner box, if you want. One can imagine that we have some box here. Okay, take its, or just take the difference of the coordinates of this point. This is the same. Contents of, I will write inner coordinates and r minus 1 contents of outer corners. And these are the care of coordinates. The care of coordinates are this one. It's evident, and this was exercise, that the number of x coordinates is the number of y coordinates plus 1. So this is the remark is as follows, so that these coordinates interlace. We have these relations, strict inequalities. Is quite obvious. So we start, maybe it's better to say where we start. We start here. We start, so this corresponds to x1. This corresponds to y1. This is x2. This point is y2, and so on. When we move in this direction, you see that this difference strictly decreases. So we get these inequalities. So there is some nice, simple, I think this will be exercise. With. So these are integers. So these are integers. Which may be positive, negative, zeros, depends. So the idea is xi interlaced corresponds to a Young diagram if and only if the sum of the x's equal the sum of the y's. Now I would like to state one more realization. The statement is as follows. So the algebra A is the algebra of super symmetric functions, again supersymmetric functions in x and maybe I will say y hat, meaning that y hat is only -1 minus. Because what I would like to say that in the conventional definition of supersymmetric functions, we don't need this because my definition of supersymmetric is not conventional one up to sign. In the conventional definition, the supersymmetric power sums are just simple differences of powers in x's and the powers in y's. So here we have just difference between powers in x and powers in y's, but because I like this change of sign, I put it in a different way. Okay? But it's not exactly the same. Actually, the precise statement is as follows, that there is some, maybe let me write it as follows, more exactly, more precisely. What I mean. Let's define this algebra sim tilde is how to say, is a little bit different specialization of the same algebra of symmetric functions. Is the algebra sim of symmetric functions. Symmetric functions only in the specialization in which the power sums from algebra symmetric functions are represented as functions as follows: the sum of minus the sum so this just mimics the A and B modified Frobenius coordinates. So these are super symmetric in conventional definition, or super symmetric in X and Y in my definition. So the claim is now as follows. The claim and proposition is as follows. Take the algebra, this algebra, and the quotient under and this quotient algebra is isomorphic to the algebra of regular functions under the map which sends this one to where these are Kirchhoff's coordinates. So we have some symmetric function on the left, essentially the symmetric function. We take its conventional superization and we substitute as the variables the Kirchhoff coordinates, and we have this relation because I already explained that the difference of X and Y Kirchhoff coordinates is equal to 0. So we have to take this, and this is an isomorphism. And how to prove this? And the result is as follows. So the idea of proof, I don't have much of time, so I would like to give the idea of proof. Is as follows. What I will prove essentially, Let's introduce another function, g, which is by definition the following. And these are here coordinates of our young diagram. So let's assign to our diagram lambda some new kind of generating function, something different. Okay. And the idea is to relate it to our initial generating function, and the result looks as follows. It turns out that the result claim is as follows. Equal to so what we have to do? First we have to prove this, okay? And next to deduce from this relations the consequence about the our claim, this one. So first, how to prove? And I propose the following trick. How to prove this idea. Use induction on, so more precisely, just consider the young graph and look what happens after some change. If you append a box, what happens? Look what happens on the left and what happens on the right. There is some rearrangement, a little one rearrangement on the left, on the right. In fact, after adding a box, this function is multiplied by a simple expression, and then we verify that the right-hand side is also multiplied by the same expression. And why this happens? This is easy to see, because look what happens in the typical case. So when we add a box here, okay, what happens? This is some point, some inner corner. It has some content C. So what happens? So this is lambda, and this is lambda plus this box. So we have some x and y. Okay, so we look only on the part, on one coordinate of x, which is c. Okay? And after this rearrangement, we obtain on the right, instead of the c, we obtained two inner corners, which are c plus 1 and c minus 1. Okay? And the c becomes some coordinate in y, new y. So we just want to analyze what happens if we remove from the x x coordinates in lambda some c and replace it by 2 new coordinates, okay? And we add to y one more coordinates number, which is equal to c. And it's easy to understand what happens. What happens here, which in this case, the rearrangement is as follows. This function is multiplied by this expression. With modification. And then we look from another side, from the same. What happens to this function under the same under the same under the same procedure, adding a box. Again, we have some modification of the same kind, and with some shift, the same happens here, and we see that it's the same. Okay? So this is a very important idea which can be used in other situations as well. So idea just what happens when we add one box, one more box, and so on, and so on, and so on. Okay? And then after that, one can prove that looking when this result is already established, one can take the logarithm and look what happens. And look what happens. And, okay, so this is just the end. So sorry, what I would like to show you. Excuse me. We get that this function, this function, let's write it as follows. I mean, pair of coordinates is equal to some factor, I forgot it, or maybe, so maybe there is some factor here, I'm probably, some factor maybe missed. I forgot, I'm sorry. I have to look at it. Some factor here, maybe. Some k or 1 over k. But what is important? What is important? It is related to, sorry, maybe there is one more. And no, there is some error. I'm sorry. I'm sorry. This is very important because there is again a shift in indexation as before for the pi functions. But here the shift is in the opposite direction. The true degree, to get some true degree in the algebra A, you have to increase the index on the left by 1. Okay? So this corresponds to the fact that the p tilde 1 does not exist. It's equal to 0. It disappears. So actually, the situation is here now that the algebra A I'm sorry, it's not very precise, but what I wrote here, sorry. Some factor. And tomorrow I will send you the corrected file, I'm sorry. So there is a shift in the opposite direction. So actually, so finally, our algebra A can be viewed as the algebra of polynomials in with conventional super power sums in the care of coordinates, but starting from index 2 and not 1, because the first function in this sense is equal to 0. So to conclude, we have five realization of this algebra of regular functions. And this is indeed a nice algebra, very useful. It's not only some definition, some construction, it's really some working tool in several examples. It gives some effective tool to prove some results. Okay, so this is the end. Let me turn off sorry.